Hello everyone, I'm Haimeng. I'm an engineer at IBM Quantum. Today I'm here to talk about quantum noise and how to characterize it on an actual hardware. I want to start by talking about a quantum circuit. So this is an object that we usually work with when we want to do any quantum computation on our quantum device. So this quantum circuit could come from any quantum algorithms you are interested in, but usually it has a certain structure. So over here, it is really a simple 4-qubit toy model. We can see that at the first step, it initialized the qubit in ground state, and then it apply a bunch of quantum operations. Over here, those are quantum gates, usually described by unitary matrices. And on our hardware, there are single qubit and 2-qubit gates that are native to our hardware that we can implement. And at the end of the circuit, we measure in the computational basis. So this is the quantum circuit that we usually work with. But bear in mind, when we actually run this quantum circuit on our hardware, all the information is processed in the physical world, and in practice, those quantum operations we talked about are not ideal. That's why we care about this topic, hardware noise. So we now understand the performance and the power of our quantum processors are still largely limited by noise. So that's why we want to understand what's the limitation of our quantum hardware as a result, so we can make the best use of it. So in this lecture, we will go over different sources of noise, and we'll go into details of incoherent noise, coherent noise, and state preparation and measurement noise. And we want to show you where you can read it from our IBM quantum platform, where we report those noise-related metrics on a daily basis. And in the end, we'll end by talking about how those metrics are experimentally characterized. And followed by this lecture, you can also join the lab session to try it out by actually doing such an experiment using Qiskit runtime. So let's come back to our circuit example and start by talking about what ideal operations should look like. So to give some examples, so first thing we noticed is there are single qubit gates. So one example is hot mod gate, which put a qubit state from ground state into superposition state. And something we can also notice is that there are rotation gates over here, which are those Rx gates over some angle. So those gates are implemented typically by turning on certain Hamiltonian. And the Hamiltonian over here for rotation gates around x-axis has the sigma x form. So those Hamiltonians are what we physically engineer and control in real hardware. And over here, this is a C0 gate. So those are the gates we use to generate 2-qubit entanglement. So here we can briefly see that with a hot mod gate and a C0 gate, we can put a 2-qubit from ground state to a maximally entangled state. So those are a few examples of how quantum operations are going to do. At the end of the circuit, the measurement operator, what do we mean by that? It is a projective measurement in the qubit computational basis. So at the end of the measurement, we will get the bit strings in classical form of 0 and 1s. So what can go wrong in all the ideal operations we just talked about? So roughly speaking, all the noise can be characterized in different categories. So the first one we're going to look at is associated with state preparation and measurement. So we call them spam errors. The second type of noise we are going to talk about today is incoherent errors. So those, in general terms, they correspond to loss of quantum information in the form of superposition and entanglement. usually due to interactions between the qubits and their environment. The third type of noise that we're going to talk about today are coherent errors. Usually they are associated with imperfect gate implementations. So this gives an overview of the lecture today. So before we jump into all the types of noise we're going to talk about, let's first quickly recap how do we represent a quantum state mathematically. So take the simplest case of a single qubit. We know a single qubit quantum state can be represented by a state vector in the two-dimensional Hilbert space. And the state vectors here we've written 0 state and 1 state forms a orthonormal complete basis for that space. So those are the two states we are going to see a lot later on. What's special about a quantum state is that besides ground state and excited state, it can also be in a coherent superposition state of the two. So how do we write a superposition state? We use what we call probability amplitudes, alpha and betas. Those can be complex numbers. And they represent, roughly speaking, probability of the state being in ground or excited state. We can, as you can see that, we have a way to visualize those quantum states on a sphere. That is what we call Bloch sphere. So if we have to talk about all available states that can be represented on this Bloch sphere, we have to talk about there is a difference between mixed state and pure state. So a pure state is what we write in this outer product form. But if we want to talk about classical mixture of pure states, that's where we have to write in this density matrix representation, where it is simply a sum of all possible pure states in this outer product form, and then weighted by this probability in the front. So this describes an ensemble of pure states. So all density matrix can be written in this block vector representation. So for single qubit case, this is how we write it. In block vector representation, we simply write the density matrix as a sum of all Pauli operators, identity matrix and Pauli XYZ. And the block vector components would correspond to the components, the coefficient in front of those Pauli matrices. So to give a few examples, if we have a plus state or minus state, those are the maximally superposition state. Those states correspond to the x poles of the Bloch sphere. So those, if we write the block vector, they would look like 1, 0, 0 as a block vector, or minus 1, 0, 0 over here. If we have ground state or excited states, I think that's pretty obvious. They are on the z poles of the Bloch sphere. There's also a very special example of a maximally mixed state, which is you have equal probability being in ground and excited states, and that corresponds to the center of the Bloch sphere. So over here, it's a quick recap of what do we mean by mixed state, how do we represent them in the form of density matrices, and how to visualize them on Bloch sphere. Later on, we'll see the effect of noise can be very well encapsulated in this picture, where we have a noise channel. And what does it do in general? A noise channel brings a pure state into a mixed state. So in the block vector representation, a pure state would have a vector length of 1, whereas a mixed state, as an output of the noise channel, would have a vector length smaller than 1. In the ideal world, we have unitary operations to describe our quantum gates. So another consequence of noise is that now the mapping from the input state to output state would have to be described by a noise channel, and we'll see specifically what does this channel do to our input states. With that, we can move on to talk about now different types of noise. So the first type of noise we encounter here is what we call spam errors, state preparation, and measurement errors. So a quick example of a mixed state here is, say, we have imperfect state preparation. That is the case where we want to prepare a state which is initialized in ground state, but in practice, we don't have the full information of the state. Then there are some population of the state ending up in excited state. So that is a type of error that needs to be captured in the model for spam errors. But in practice, spam errors and readout errors are usually very hard to be separate from each other. So we use this spam error model to capture them together. So a consequence of state preparation and measurement errors is that after measurement, we will get noisy bit string probability distributions. What do I mean by that? So suppose we have an ideal GHZ state for 4 qubits. So the grain distributions here corresponds to the ideal case. But due to imperfect state preparation and measurement errors, we can get bit strings that are away from this ideal distribution. So mathematically, the noisy distribution and ideal distribution can be related in this form over here, and the effect of spam errors can be captured by this A matrix. So in this probability vector here, each index describes the probability of measuring bit string I that corresponds to the ith element of this probability vector P. Whereas each index, each element in this A matrix, for example, the ith row, jth column, corresponds to the probability of observing state J given the state is being prepared in I. So experimentally, we can try to characterize this A matrix, which would give us an idea of how much spam errors there are over here. So over here on the bottom right, we can see an example of such an A matrix. Usually it is very challenging to characterize this A matrix at scale because we can see that it has 2 to the n by 2 to the n elements, where n is number of qubits. That's why there has been ongoing research to try to figure out how to characterize spam errors at scale. But on our backend, we report this property, this what is the probability of measuring state 0 if the state is prepared in 1. This property, we report them qubit by qubit on our backend, and you can check it out on our IBM quantum platform. But in principle, bear in mind that those readout errors and state preparation errors could also be correlated. So with that, we can see from the backend that the typical readout error is on the order of 10 to minus 2. So that is the readout error we have on our backend. And moving forward, I would like to talk about incoherent errors, which are captured by this picture of noise channel. So over here, what we see is we have an input state row and the output state after the noise channel is denoted by rho prime with this map epsilon acting on rho. So mathematically, we have a bunch of options to represent this noise channel, and one of them is what we call Krauss representation. So this is the mathematical form of it. Basically, we will have a set of Krauss operators to act on state rho. The effect of noise, what does the noise do to the state, will be captured by those operators. And of course, there are some constraints on how this map should be like. Some properties include that this map should be linear, should be complete positive, and trace preserving. Basically, those properties enforce that this map maps a physically relevant density matrix to a physical density matrix. If you're curious to learn more about noise channels rigorously, I would refer you to this lecture on quantum channels by Zhang, which is available on IBM Quantum Learning platform. Now we can see several examples of incoherent errors, and we will see later those examples are actually quite relevant when we want to understand noise that are actually going on our quantum hardware. So the first example is the energy relaxation process. So this is a process which brings, as the name suggests, corresponding to the decay of the excited state to ground state. This process is quite relevant for superconducting qubits, which is the hardware we're talking about here, because the qubits we are talking about operate at very low temperature, typically around 20 millikelvin, and our qubit frequency is typically between 4 to 6 gigahertz. Given that, it's quite intuitive to say that there's a much stronger decay from excited state to ground state compared to the opposite process from ground state to excited state. So this timescale of energy relaxing from excited state to ground state is characterized by T1. That is what we refer as the relaxation time. And that relaxation time can also be associated with a probability of a relaxation error for some evolution time t. So if we want to mathematically describe this energy relaxation process, we can use what we call a amplitude damping channel. And over here, we can see the cross operator form of this channel. But basically what this channel does is that it takes an excited state to ground state with probability p, whereas it leaves the ground state unchanged. If we visualize the action of this amplitude damping channel on the Blocksphere, we can see what it does is that it brings all the state and contrive it to the ground state. So at the end, the steady state of this channel would be the ground state. So the picture we're getting here is that ground state is actually a long-lived state that is largely unaffected by this type of relaxation errors. Other state would be suffer from this T1 limit. Another type of noise we'll be talking about is dephasing noise. So that is the process where superposition states become classical mixture and a coherent state lose its phase information. So similarly to the picture we had before for T1 relaxation, the dephasing timescale here is characterized by what we call T2, and T2 can also be related to a dephasing error rate by this equation here. We can see that both relaxation and dephasing error has a consequence of turning quantum information to classical information. So this dephasing channel this dephasing process can also be mathematically described by a dephasing channel. And over here, we can see the cross operator form of it. The action of a dephasing or phase damping channel on the Bloch sphere is that it shrinks the size of the x and y component of the Bloch vector. Hence, we will see that now the quantum states in this Bloch vector representation would have a vector length of smaller than 1, and it has less and less information about its phase. So those two processes, the energy relaxation and dephasing, are both two physical relevant decoherence process on our hardware. Another mathematically motivated noise model is what we call polynoise model. We'll see that it has a form like this for single qubit case. What it does is that it apply the single qubit poly operators to the qubit state at each given probability. So this is also a physically motivated noise model, and it has actually been used to model our noisy quantum processors in practice, given by this literature here. And this paper showed that one can use certain tomography or learning technique to learn the parameters associated with polynoise channel for a given device. A special case of polynoise model is what we call depolarizing channel. That is the case when the probability of XYZ poly operators are the same. So this channel can also be written in the following form over here. So what the depolarizing channel does is that with probability P, it maps the state to the maximally mixed state, and with probability 1 minus P, it leaves the state unchanged. So this is a formula directly suggesting depolarizing channel is a special case of poly channel given X, Y, Z poly operators have the same probabilities. So poly channels, we can see what's special about those channels are the steady state of both poly noise channel or depolarizing channel as a special case is that its steady state is the maximally mixed state. That's why we say those channels are unital, meaning that it maps an identity to an identity in a maximally mixed state to itself. After talking about different types of incoherent noise, now let's move over to talk about coherent errors. So as we mentioned, coherent errors are usually associated with imperfect gate implementations. So in our hardware, gates are usually generated by turning on certain Hamiltonians that we can control and engineer. So let's look at a single qubit case where we have a single qubit rotation gate around x-axis. Suppose we want to implement an x gate, and that corresponds to rotation around x-axis of angle pi. What we do in practice is we would turn on this Hamiltonian of sigma x form with amplitude v, and we calibrate the rotation axis and the rotation angle corresponding to the desired angle. But what if we engineered the wrong Hamiltonian? Suppose we have incorrect phase specified in the microwave generator that corresponds to some component of rotation around y-axis. Or suppose we have poorly calibrated our pulse duration and our pulse angle is not corresponding to angle pi. So in those two cases, the coherent errors can be modeled by unwanted unitary gates in a circuit. In the case of misalignment, a noisy X gate with coherent errors can be decomposed into an ideal X gate together with a Y rotation gate that corresponds to rotation around Y-axis with some small angle. In the case of miscalibrated pulse durations, the noisy X gate can be decomposed into the ideal X gate together with a X rotation gate with an over or under rotation angle. So that's the case where we can model coherent errors. In the case of 2-qubit coherent errors, that is the case where we usually deal with what we call crosstalk errors, and this has something to do with how 2-qubit gates are implemented. Take the case of Eagle processors, where our native 2-qubit gates are what we call echoed cross-resonance gates. And they are equivalent to a CNOT gate up to some single qubit rotations. So what does ECR gates look like? So in practice, what we implement is a Hamiltonian of the ZX form. So those are the interactions we use to generate entanglement between 2 qubits. So in the echoed cross-resonance gate, we implement RZX rotations with opposite amplitude, pi/4 and minus pi/4 back-to-back, with some single qubit RX rotation gate in between. So that whole sequence implement an ECR gate. But we can see that the full Hamiltonian describing this gate evolution actually has some unwanted terms. So those unwanted terms would correspond to coherent errors if the calibration part is not done perfectly. So special attention is usually paid to this form where we have ZZ coupling between 2 qubits. And in our device, specific to Eagle processors, those ZZ coupling are actually resulted from static capacitive coupling that cannot be completely turned off even when the gates are not implemented. So those type of coupling can result in unwanted crosstalk between the target qubits to the nearest neighboring connected qubits. So those are a source of crosstalk errors that we have to deal with. Also, bear in mind that the cross-resonance gates we're talking about here are usually way longer than single qubit gates. That means our 2 qubit gates has a way longer, usually hundreds of nanoseconds of gate duration. So that's why usually 2 qubit gates are considered the main source of error in the context of the whole circuit. After talking about single qubit and 2 qubit coherent errors, I want to quickly summarize by an observation that coherent errors oftentimes result in oscillations in signals. To see this, I would refer you to an example in our last year Qiskit Global Summer School, where we look into a case in simulation to take account of single qubit over-rotation error, depolarizing error, and spam errors. So for this example, showing on the right here, the ideal expectation values for the observable single qubit Z would always be either 1 or -1. And we can see how under the simulated noise, the signals diverge from that. And we can see due to this single qubit over-rotation error, we see oscillations in the signal. So if you do see signature of unwanted oscillations, that could possibly indicate the presence of coherent errors in your experiments. And from this example, we can also see that coherent errors can build up much more rapidly than incoherent errors, at least in short time. So they can be very undesirable and tricky to deal with. There are a number of techniques that can deal with coherent errors. For example, dynamical decoupling and twirling. If you're interested in those techniques, I refer you to the lecture from this year's summer school on execution on noisy quantum hardware, fighting errors before fault tolerance by my colleague Pedro. So now we have talked about both incoherent noise and coherent noise. With that, let's put what we have talked about in practice and look at the following example, where we want to implement a 6-qubit circuit on a chain of physically connected qubits. And the information we have here is that, first of all, suppose we know one of the qubits, qubit 2, would have really bad T1, T2 time, hence very low coherence time. And we also know ECR gates or 2-qubit gates are not desirable to implement in parallel due to crosstalk errors. So those information can actually inform us to schedule our gates in a logical circuit in a more noise-resilient way. What do I mean by that? Suppose in this 3 examples, we are implementing exactly same circuit in the ideal case. But in order to avoid crosstalk between qubit 1 and qubit 2, which are physically connected, we can also try introduce a barrier in between those two 2-qubit gates so that those 2 pairs of 2-qubit gates are not implemented in parallel, hence reduce crosstalk errors as much as possible. Another information we had was if qubit 2 has low coherence time, what we can do is we can delay the implementation of ECR gates to as late as possible so that qubit 2 stay in ground state for as long as possible before engaging in any active computation. So this is a nice example where using our understanding of incoherent noise and coherent noise, how we can come up with optimal ways to schedule our circuit. And this is what we call as late as possible scheduling strategy. If you want to read more about that, I would refer you to this paper here below. So far we have mostly talked about local noise for single qubit and 2-qubit case. So in the following, I want to briefly present the picture of how those noise can propagate in time and space. So suppose in the picture of a layered circuit, and over here what we're seeing is that we're implementing layers of 2-qubit gates. And those layered circuits are actually quite relevant in applications of near-term quantum computing. So this particular case, we are looking at brickwork random circuit on a 1D chain. So it has been derived theoretically that if we have random 2-qubit gates and all noise are local, then the output of this noisy circuit would converge fast to maximally mixed state. And the noise model in the deep circuit regime can actually be very well approximated by global depolarizing noise. So although this is only true for random circuits, but it can also speaks to the limitation of running circuits on an actual hardware. So there's a limit on how deep we can run circuits before a quantum state becomes maximally mixed state, hence purely classical. In previous slide, we are interested in what's the output state of a noisy quantum circuit. But in a lot of applications, we are only going to measure the sum observable and estimate its expectation values. Suppose the observables we are interested in are local, meaning we are only going to measure a subset of qubits. In this case, we are only going to measure observable on a single qubit. And it has been, our understanding over here is that the effect of noise can be more moderate than the case we presented before. The intuition here is that only the noise in a specific region of the circuit is going to contribute to the error in the final expectation values. And this region is what we refer to as a light cone. This is, over here we are drawing what we call a backward light cone. That is, if we start from the back of the circuit, from the measurement, and we back propagate the observable and shade the region where the wires are physically connected to this qubit that is measured. And we can, if we keep doing this backwards, we can shade the entire region. And within this region, those errors are going to contribute to the expectation values. This is pointed out in the paper referenced below, and using this intuition, we can argue that the noise or the errors in local observables is going to be less than a general observable on all qubits. So far, we have looked into single qubit, two qubit, incoherent and coherent noise, and how they can propagate over circuits in a theoretical setup. But how do we figure out and characterize noise in practice is a different question. So in the following, we'll look at how noise can be experimentally characterized. To understand that, I want to first start by talking about how do we characterize an unknown quantum state, and then we'll talk about how do we characterize an unknown quantum process. So take the example of a single qubit. We can expand the single qubit density matrix in the Pauli basis as the following. So by a simple counting argument, we can see that in order to measure all the coefficients corresponding to those Paulis, we need to perform at least 4 to the n minus 1 measurements, where n is number of qubits. Minus 1, it is because we know trace of rho is 1, so we can save 1 measurement. So in order to, in general, to characterize an unknown quantum state needs exponentially number of experiments. What about the case where we are interested in characterizing an unknown quantum process? It turns out the procedure of characterizing an unknown process is the following. First, we prepare 4 to the n input states, and then we pass it to the quantum channel that we want to characterize, and then we measure in all 4 to the n complete bases. By this simple counting, we can see that we need on the order of 16 to n experiments to characterize an unknown quantum process. So that is even harder than doing state tomography. So it has been an ongoing research topic in making this scalable. But from this, we have learned that characterizing a process in general is quite costly. But experimentally, we can use a trick of randomization. That is, we use random gates in order to impose certain symmetry over the quantum channel. Hence, we do not need to do that many experiments. So in practice, that is what randomized benchmarking is trying to do. So over here, I'm showing a simple single qubit, two qubit randomized benchmarking protocol where we implement layers of random Clifford gates where Ci are single qubit or two qubit random Clifford gates sampled from a finite Clifford gate set. The final layer of the randomized benchmarking sequence implements an inverse operation, where the total sequence, in the ideal case, corresponds to an identity operation. And then, after the whole sequence, we measure the probability of the state getting back to the ground state at the end of the sequence. In the whole randomized benchmarking experiment, we vary the sequence length m, and we plot this state survival probability as a function of m. In order to extract error rate per gate from RB experiments, we fit the survival probability to an exponential of the following form. Note that this exponential decaying form we're fitting to is actually derived under the assumption that the noise model follows the depolarizing noise model. So after fitting and extract the parameter alpha, which corresponds to the error rate in a depolarizing noise model, we report the average gate error of the following form. And the average gate error can also be related to average gate fidelity or the process fidelity, which is more mathematically well defined. The RB experiment is actually how we characterize single qubit gate error and ECR gate error for backends. And those metrics are reported on our IBM quantum platform over here, and you can check those numbers for different backends. Over here, something to note that is that the 2-qubit ECR errors for ego device, in this case IBM Sherbrooke, is an order of magnitude larger than single qubit gate errors, which is saying the 2-qubit gate errors are actually the main source of error when we want to implement circuits. A limitation of randomized benchmarking protocol is that it is insensitive to coherent errors due to randomization. Motivated by that, we have been using a new metric, what we call layer fidelity, or error per layer gate, in order to capture the effect of crosstalk errors. So this new metric, layer fidelity, is defined over, say, n connected qubits. Similar to what we've shown on the figure here, we are concerned with a set of connecting gates defined over those qubits that form an entangling Clifford layers. And we ask, what is the process fidelity of this layer of gates? As we have talked about, those layer structure are quite relevant, and they serve as building blocks for a lot of circuits we care about. And this layer fidelity includes crosstalk and can be related to some other metrics to infer the error mitigation overhead. In doing experiments, the layer fidelity experiments actually expands on the randomized benchmarking protocol. So we'll see how the circuits will look like if we want to measure layer fidelity. So first, in layer fidelity experiments, we want to define a layer structure over some physically connected qubits. In this case, it is a 1D chain of 10 qubits. And the next thing we do is we want to separate this layer structure into disjoint sets and measure with randomized benchmarking protocol individually for each disjoint set. That is what the step 3 is for. So for each layer, we will do simultaneous direct randomized benchmarking experiment with barriers for each layer. In those disjoint sets, the properties that each qubit would only have one 2-qubit gate being applied on. At the end of this protocol, we'll get a bunch of fidelities from doing RB experiment, and the layer fidelity reported is simply multiplying those fidelities together. So this is the expression for the EPLG metric, error per layer gate, we report. It is simply 1 minus layer fidelity up to 1 over n, where n to q is number of 2-qubit gates in the circuit. So what's nice about this metric is that it allows us to compare EPLG to the error per gate measured in isolated RB experiments. By comparing those two sets of data, over here, solid dark blue for layered fidelity experiment and light blue for isolated standard RB experiment, we can already see the effect of crosstalk error. So the takeaway here is that when the error per layer gate is characterized in the context of a layer structure, the gate fidelity or the gate error tends to be worse. So we get a higher gate error in those layered context, whereas when they are being measured separately, they have a less error rate, which agrees with our intuition that gates, 2-qubit gates should be run separately rather than in parallel. Over here, if we compare different processors, blue for Eagle processor and red for Heron processor, we can see that the difference in comparing layered fidelity experiments versus standard RB experiments is less. That is because our Heron device suffers less from the crosstalk error. So the EPLG metric is actually a measure we can use to capture continuous improvement of our hardware. With that, I would like to point you to our backend property where this EPLG metric is reported, in this case for IBM Torino. And this is where you can check what's the EPLG for each backend, and in this case it is 0.8%. If you're interested in characterize this metric on your own for different devices you care about, I would encourage you to join the lab session where we would actually run a layer fidelity experiment via Qiskit runtime led by my colleague Samantha. So with that, I would thank you for joining us today and hope to see you soon.